Let's say if we have the derivative of x to the third power plus 4x plus 3. How do we solve this? Well, one thing to know is that the derivative of a sum is equal to the sum of the derivatives of the individual components. So in this case, I can actually break this up into 3 different parts. So in this case, I can actually break this up into the derivative of x to the third power plus the derivative of 4x plus the derivative of 3. All right. So when you're dealing with derivatives and you're adding, or you can be subtracting, right? So you're adding or you're subtracting. Well, it turns out that the derivative of this whole entire thing is equal to the sum of the derivatives of each individual component, like so. Now, in order to solve this, well, you got to know something called the power rule, which states that the derivative of, let's say, with respect to x of x to the n power gives you n times x to the n minus 1. So if I have, let's say, the derivative of, if I'm trying to find out the derivative of x to the fourth power, what I essentially do is I bring down the exponent. So it's going to be 4 times x, and I subtract 1 from the exponent. So 4 minus 1 is 3. So the derivative of x to the fourth power is 4x to the third power. I bring down my exponent, and then I just subtract 1 from the exponent, like so, right? Bring down the exponent, subtract 1 from. When you're doing the power rule, it's important to know that your exponent right over here, can't be like, x. It can't be like another variable or another function in terms of x. So for example, if I have something like x to the x power, I can't do the power rule on this. I cannot do the power rule on this. But if I have something like x to the 2.5 power or x to the, let's say, the -1 power, then I can use the power rule. So you can't do it if your exponent is containing some sort of variable, another kind of x in the example before. So just make sure to look out for that. Now, in this case, we can just apply the power rule to each one of these terms. So what's the derivative of x to the third power? Well, you bring down the exponent, so it's going to be 3x, but then you're going to subtract 1 from the exponent. So 3 minus 1 gives you 2. All right, what about the derivative of 4x? Well, you can think about this as 4x at first power. So you bring down the exponent, so it's going to be 1 times 4x, right? But then you have to subtract 1 from the exponent. So 1 minus 1 gives us 0. X to the 0th power is just 1. So this is just going to be equal to 1 times 4, which is just 4. Finally, what's the derivative of 3? Well, you can think about this as 3 times x to the 0th power, right? So you're going to bring down the exponent. So this is just going to be equal to 0 times 3x, right? And you're going to subtract 1 from the exponent. So this is just going to be 3 times x to the -1 power. And 0 times whatever this is just 0. So this is just going to be plus 0. And in conclusion, your answer, the derivative of all of this stuff above, is just going to be equal to 3x to the second power plus 4. And there's the answer. So another key thing to kind of know is that if you're taking the derivative of a constant, it's just going to be equal to 0. So a constant refers to kind of any term without an x. So for example, 3, 4, -1, right? Any one of these terms, the derivative is just going to be equal to 0. If I have the derivative of, let's say, the square root of 2, well, this term doesn't have an x, right? So this is just going to be equal to 0. The derivative of, let's say, -3, this term doesn't have an x, it's constant, so it's just going to be equal to 0. Now, why is that? Why do you think the derivative of a constant is equal to 0? So let's say if I have the function f of x, and I'm trying to find a slope at this point. Let's say it's x equals -2. Let's say if I have f of x plus 3, and I'm trying to find the slope at x equals 2. So they're the same x value right over here. And notice how f of x plus 3 is literally just the exact same function as f of x, except you move everything up by 3. Now, if we're trying to find the slope of the line at this point, notice how like the slope of the line actually does not change with this plus 3. Whenever we add a constant term to our function, all it does is it moves the function up and down. But it doesn't actually change the slope of a function at any single point, right? If I selected this point, for example, the slope would look something like this. And notice how it's literally the exact same slope at this function right over here, right? The slope doesn't actually change when you add a constant term. All you do is literally just move the function up and down. But the slope itself, which is the derivative, right? The derivative represents the slope at a certain point. So if, this plus 3 right over here doesn't do anything to the slope, well, its derivative is just going to be equal to 0, right? It's not going to have any effect to the slope. It's going to have 0 effect to the slope. Another way you can kind of think about it, a simpler way to think about it, is if you have, let's say, y equals mx plus b, right? That's the equation for a straight line. So let's say if I have y is equal to 3x, or let's say I'm comparing this to y is equal to 3x plus 2. Notice how the slope of a function is the same, and this constant term at the end does not affect our slope. All right, so that's another way you can think about it, right? This plus b term determines our y-intercept, right? It kind of moves the function up and down, but it has no effect on our slope. The m term is what determines. Find the derivative of this right over here, 1 divided by x to the third power. Well, you can actually rewrite 1 over x to the third power as x to the negative 3 power. So this is the same thing as the derivative of x to the negative 3 power, using properties of negative exponents. So now what you can do is you can just apply the power rule. So you bring down the exponent, so it's just going to be negative 3 times x, and you subtract 1 from the exponent. Negative 3 minus 1 just gives you negative 4. So the derivative of this is just going to be negative 3 times x to the negative 4 power, or you can rewrite it as negative 3 divided by x to the 4th power, because once again, you just bring the exponent down due to negative exponent properties, and you get this. What if we have the derivative of x to the 3rd power times sine of x? Whenever you have the derivative of two functions, and both of the functions have an x in them, it's going to be equal to the first function times the derivative of the second function plus the derivative of the first function times the second function. So it's kind of like you take the derivative of one of them, leave the other one the same, take the derivative of the other one, leave the other one the same. So in this case right over here, right, you can think about this as, you can think about f of x as equal to x to the 3rd power, and g of x. So in this case, you can think about f of x as equal to x to the 3rd power, g of x is equal to sine of x. So what you're going to do is you're going to leave kind of the first function intact. So it's going to be equal to x to the 3rd power, right? So just leave the first part intact. Then you take the derivative of the second part. So the derivative of sine of x is equal to cosine of x. Then this is going to be added. To the derivative of now the first part. So now you kind of switch it up a little. So it's just, so the derivative of x to the 3rd power, 3x to the 2nd power using the power rule. And you leave the second function intact. And there we go. That is the derivative of our function. So you keep the first part, then you take the derivative of the second part. Then you take the derivative of the first part, and then you leave the second part. So you kind of do the opposite of what you did kind of in the first place. For example, if we want to find out the derivative of 4x to the 3rd power times cosine of x, well, what we do is we keep the first part, right? So we keep the first part normal. We differentiate the second part. So the derivative of cosine of x is negative sine of x. And then you add it to the derivative of the first part. What's the derivative of 4x to the 3rd power? Well, we can use the power rule to solve this. What you do is you bring down the exponent, so it's just going to be 3 times 4x, right? You bring down the exponent, and you subtract 1 from the exponent, so 3 minus 1 is 2. 3 times 4 is 12. So the derivative of 4x to the third power is just going to be 12x to the second power. And finally, you keep the second function. So it's just going to be cosine of x. So yeah, keep the first one, differentiate the second one, then differentiate the first one, and then keep the second one. And then there's the answer, or you can move this negative sign to the front, and there you go. I mean, if your teacher wants you to, you can also like factor out 4x to the second power, but you can also keep it this way if your teacher allows you to, All right, so let's say we want to find the derivative of x squared minus 1 divided by x minus 3. Notice how you have two functions, right? You can say this is the first function, f of x, and you can say that this one on the bottom is g of x. So when you have two functions that are divided by each other, and both of them have an x in them, well, you can use the quotient rule. Now this isn't the quotient rule, this is actually the product rule. But the quotient rule is actually very similar to the product rule. So this right over here is the product rule. But the quotient rule, however, is very, very similar. Now, notice how it's literally basically the product rule, except the plus turns into a minus, and then you have a g of x squared at the bottom. That's basically, if you remember the product rule, then it's much easier to remember the quotient rule. So let's do it. So the quotient rule, you keep the top function, so you're going to keep the f of x. So you're going to keep the f of x. And then you're going to multiply it by g prime of x. So you're going to multiply it by the derivative of g of x. G prime of x is just the same. It's the same thing as the derivative of g of x. So we know that g of x is just x minus 3. So it's just going to be the derivative of x minus 3. And this is going to be subtracted by f prime of x. So now you differentiate the top function. So now it's just going to be the derivative of the top function, which we know is x squared minus 1. All right, I had no space, so I just copied and pasted it down here. So it's just going to be the derivative of the top function. So it's going to be the derivative of a numerator times the denominator regularly. So it's just times the regular old denominator. And you divide all of this by g of x squared. G of x is x minus 3, so it's just going to be x minus 3 squared. Now let's solve. So what's the derivative of x minus 3? You can use one of our first derivative properties that we've two things that you're differentiating is equal to the two things differentiated subtracted from each other. So basically you get that this is going to be equal to, the derivative is going to be equal to 1 times x to the 0th power, right? Because using the power rule, remember, you subtract 1 from the exponent, so 1 minus 1 is equal to 0, and you have to bring the exponent down, so this is just going to bring the exponent down. So 1 times x to the 0th power, x to the 0th power is 1, so it's just 1 times 1 is 1. And you subtract this from, well, the derivative of a constant term is just going to be equal to 0, so 1 minus 0 is 1. Therefore, the derivative of x minus 3 is going to be equal to 1. All this is just going to be equal to 1. What about the derivative of x squared minus 1? Well, let's do it. So derivative of x squared minus 1, that's just going to be equal to the derivative of x squared minus the derivative of 1. Derivative of a constant is 0, and the derivative of x squared is just going to be 2x. You bring the exponent down, so there's the 2, and you subtract 1 from the exponent, so 2 minus 1 is just 1, and 2x minus 0 is just 2x. So there you have it, 2x. And now all you need to do is kind of simplify this. So the first part, you have x squared minus 1 times 1, which is just the same thing. So you have x squared minus 1, and you're subtracting this by, put this in parentheses. So you have x squared minus 1, and don't forget you're subtracting this by 2x times x minus 3. So 2x, that's going to be 2x squared. And then after that, 2x times negative 3 is minus 6x. all of this is divided by x minus 3 squared. Now let's simplify this. So you distribute the negative sign, you get x squared minus 1 minus 2x squared plus 6x. And now all divided by this, but I'm too lazy to write it out. So let's just simplify the numerator first. Negative x squared. This is going to be negative x squared. Let's see. Plus 6x minus 1 divided by x minus 3 squared. And, there we have it. We can also expand out the denominator. So we can say this is negative x squared plus 6x minus 1 divided by x squared minus 6x plus 9. Other than that, that's looking pretty good. The derivative of 3x squared plus 1 to the 5th power. Now, in order to solve this, you need to know something known as chain rule. Chain rule is definitely by far one of the most confusing rules. So, the first thing you got to know is what a composite function is. What is a composite function? And it's basically a function inside of a function. So you might have seen this before. If I have like f of g of x, for example, that is a composite function. Now, when you have a composite function and you're trying to take the derivative of a composite function, it's just going to be equal to f prime of g of x times g prime of x. It looks very confusing at first, but we'll do some examples. In this case, if this part right over here, if this function right over here is a composite function, well, what can we put as f of x and what can we put as g of x, right? So this right over here is a composite function, because imagine this, right? Imagine if we have f of x equal to x to the 5th power. And imagine if we have g of x equal to 3x to the 2nd power plus 1. So that means that f of g of x is just going to be equal to, well, we know that f of x is x to the 5th power. So f of g of x, well, everywhere we see an x, we replace it with a g of x. So it's basically substitution, right? If we take a look at x to the 5th power, and we want to find out what f of g of x is, everywhere we see an x, just replace it with a g of x. So it's just going to be 3x to the 2nd power plus 1, and all of this is to the 5th power, right? We just substituted x with 3x to the 2nd power plus 1. So this is a composite function right over here, because it's basically a function inside of another function. Now that we've identified what's our f of x and what's kind of our g of x, we're able to solve this. So the first step you got to do is you have to identify, okay, so our f of x so remember, your f of x represents the outside function. So your f of x represents the outside function, right? X to the 5th power, this 5th power is this outside function. And the g of x is the inside function, right? The g of x is this inside function we have right over here. All right, so f of x is outside function, g of x is your inside function, right? Because g of x is inside f of x. Now, what you do, the first step is you differentiate f of x like normal. So let's say if we want to find out the derivative of f of x. So we want to find out the derivative of x to the 5th power. How would we do this? Well, you use the power rule, and it's just going to be equal to 5x to the 4th power. Bring the exponent down and subtract 1 from it. Now, if we know that f prime of x, or the derivative of f of x, is equal to 5x to the 4th power, well then what's f prime of g of x? What's this going to be equal to? Well, everywhere you see an x, you just replace it with a g of x. So this right over here is just going to be equal to 5 times, well, we know g of x is 3x squared plus 1. And all of this is going to be to the 4th power. All right, it's this f prime of g of x, it's not as complicated as you think. All you do is you take the derivative of the outer function and And, well, you just replace all the x's you see with the inner function, right? You're taking the derivative of the outer function with respect to the inner function. Replace all the x's with this inner function right over here. Now, you're just going to multiply this. Now what you do is, so I'm just going to write this over here. So you have 5 times 3x squared plus 1 to the 4th power. Now what you do is you multiply by the derivative of the inside function. So the derivative of, in this case, our inside function is 3x squared plus 1, right? So the derivative of, it's the derivative of the inside function, 3x squared plus 1. And this is just going to be equal to 6x. So your final answer is just 5 times 3x squared plus 1 to the 4th power times 6x. Or you can rewrite this. You can combine these two terms together. So it's just going to be 30x times 3x squared plus 1 to the 4th power. I mean, you can expand this once again, but I'm a little too lazy, so I'll just write it like this. Looks very scary at first. How do we do it? Well, what's the outside function going to be equal to, and what's the inside function going to be equal to? Well, you can think about our outside function as the square root of x. Our outside function is the square root of x, and the function on the inside, is 3x plus 1. Think about it, right? If f of x is equal to the square root of x, and g of x is equal to 3x plus 1, then f of g of x is just going to be, well, everywhere we see an x, we replace it with a g of x, right? Everywhere we see an x, we replace it with a g of x. So it's just going to be the square root of 3x plus 1, which is what we have here. So we're dealing with a composite function, meaning that we have to use the chain rule. So I'm just going to write this out again. So how do we do this? Well, first, you want to take the derivative of f of x. So you first want to find the derivative of this outside function, right? So the square root of x. Now, what's the derivative of the square root of x? I haven't really talked about this yet. Well, you know that the square root of a number can be written as that number to the 1/2 power. So I can actually rewrite this as x to the 1/2 power. Now I'm still taking the derivative of it. And now I can use the power rule. So now what I do is I bring down my exponent. So I'm going to have 1/2 x, and I'm going to subtract 1 from the exponent. So it's just going to be negative 1/2. And I can rewrite this as 1/2 divided by the square root of x, right? Because the negative exponent brings the x down. So it's just going to be x to the 1/2 power in the denominator. And that can be rewritten as the square root of x. So then I can just rewrite this as, well, it's just going to be 1 divided by 2 times the square root of x, right? And, I mean, in case you didn't understand this step, I'll just show it to you real quick. This thing right over here can be rewritten as 1/2 divided by the square root of x. When you're dealing with fractions, you can think about this as the square root of x over 1. So, you know, when you're dividing by this, keep, change, flip. 1/2 times 1 over the square root of x. It's just going to be this, right? You just multiply the denominators together. So now we have the derivative. We have the derivative of our outer function, right? We have the derivative of our outer function. So now all that's left to do is everywhere we see an x, just replace it with the inner function, which is 3x plus 1, right? So it's just going to be, so if we want to find f prime of g of x, everywhere we see an x, we just replace it with a g of x, right? And we know g of x is 3x plus 1. So it's 1 over 2 times the square root of 3x plus 1. And now all we have to do is just multiply. Now all we have to do is just multiply all of this by g prime of x, or the derivative of the inside function. So the derivative, so it's just going to be, it's all multiplied by the derivative of the inside function. We know the inside function is 3x plus 1, right? That's what we put as our g of x. So the derivative of 3x plus 1, that's just going to be equal to 3. So it's just going to be 3 divided by 2 times the square root of 3x plus 1 in the denominator. And there we have it. That is our derivative using the chain rule. Use the chain rule for this problem. So imagine if our outside function is equal to e to the x. Our outside function is e to the x. And our inside function is equal to sine of x. So that means that f of g of x is equal to, well, you have e to the x, but everywhere you see x, you just replace it with a g of x, which is sine of x. So yeah, this checks out that this is a composite function. Now, first step, when you're using the chain rule, you take the derivative of your outside function. And it actually turns out that the derivative of e to the x is equal to itself. So that is also something important to know. The derivative of e to the x is literally itself. And now all you have to do is everywhere you see x, right, you just replace it with a g of x. So it's just going to be e to the sine of x, right? And then you multiply this by the derivative of the inside function. The derivative of the inside function, aka g of x, that's just going to be equal to cosine of x. And there we have it. That is our answer. Our outside function is x squared, and our inside function is x squared plus 4, right? That's on the inside. X squared, that's on the outside. The derivative of x squared is just going to be equal to 2x using the power rule, right? Drop the exponent down, subtract 1, which means that f prime of g of x, well, everywhere you see x, just replace it with a g of x. So it's just going to be 2 times x squared plus 4, right? Because that's g of x. Just replace everything with x with this. And then don't forget to multiply this. Don't forget to multiply this by g prime of x, aka the derivative of all of this, derivative of x squared plus 4, which is just 2x. And boom, there's our answer. We can simplify this a little bit. First, you can just distribute. You get 2x squared plus 8. Then you multiply 2x by all of this. So you get 4x to the third power plus 16x. And there's our answer. So we have learned how to do, let's say, the derivative of x squared when your base is a variable and your exponent is a constant. Or we know how to do, let's say, 2 to the sine of x, where the base of your exponent is a constant, and then your exponent itself is, a function in terms of x, right? For this problem, you would just do the chain rule, and for this problem, you can just do the power rule. But what happens if I want to take the derivative where the base and the exponent is both a function in terms of x? How would we do this? And there's actually 2 ways of doing this. Note that x is equal to e to the ln x. Because e, you can I'm gonna write over here of e, and then we have ln. Ln is just log base e, and in this case is of x. All right, and whenever you have, I'll just y to the log base y of x, this is just going to be equal to x itself. So in this case, when we have e to the log base e of x, that's just going to be equal to x. All right, meaning that x is equal to e to the ln x, because this e and this ln basically cancel out because they're inverses of each other, right? So then you just get x itself. So I'm gonna just do that right over here. I'll just write this function. This is the derivative of e to the ln of x raised to the x power, right? All I did was I put this this x right over here as e to the ln of x, because I know that these two things are equal to each other, right? As we stated above. One property of logarithms is that you're able to bring the exponent down. So this is the same thing as the derivative of e to the ln of x multiplied by x. So I'm just going to do that like this. X ln x. Right, I just bring the exponent down, so it's just going to be x times ln of x. Now, notice how this is a composite function, right? You can think about the outside function as e to the x, and then now you can think about the inside function as x ln x, right? So now this is a composite function. It's a function inside of a function, meaning that you can use the chain rule now. So remember the chain rule? You have f prime of g of x is going to be multiplied by g prime of x. So in this case, what's the derivative of e to the x? That's just going to be e to the x, right? It is its own derivative. So if we know that f prime of x is equal to e to the x, well, what's f prime of g of x? Well, everywhere we see x, we just replace it with a g of x, right? Everywhere we see x, we replace it with a g of x. So it's just going to be equal to e to the x ln x, right? Now, don't forget that when we're doing the chain rule, we have to multiply this by the derivative of g of x, the derivative of g of x. So it's just going to be multiplied by the derivative of g of x. We know that's x times ln of x. So it's going to be multiplied by all of this right over here. Now, what is the derivative of x times ln of x? Well, you have two functions multiplied together, right? Now in terms of x. And we have these two functions multiplied together, you have to use the product rule. So yeah, sometimes when you're doing the derivative problems, you have to use more than one rule, you know? So in this case, this is just going to be equal to, well, e to the x ln x, that's just the same thing as x to the x, right? We kind of like established that before, that you drop down the exponent. So the derivative of x to the x, this is the same thing as the derivative of e to the x times ln of x, right? We just said how that's the same thing. So I can just rewrite e to the x times ln of x as x to the x power. It's going to be multiplied by, and then you have to use the product rule for this. So the product rule, so the derivative, it's just going to be the regular first function times the derivative of the second function. The derivative of ln of x is equal to 1 over x. That's something you got to remember. And this is going to be added to the derivative of the first function, which is just 1, right? Because you have x to the first power rule, bring down exponent, subtract 1. You get 1 times x to the 0th power, which is just 1. And you have the same old second function. So 1 times ln of x, which is just ln of x. Right over here, we can simplify things a little bit. X times 1 over x, that's just going to be equal to 1, right? Because the x's kind of like cancel out. So now all we have to do is we just distribute the x to the x power to everything, right? So it's just going to be x to the x plus x to the x ln x. And that's our answer. Let's say that we have y is equal to x to the x power. Let's say we have y is equal to x to the x power. If we take ln of both sides, so I'm just going to highlight this right over here. Let's say we have y is equal to x power. If we take ln on both sides, this is the same thing as ln of y is equal to x ln of x, because we're able to bring down the exponent due to the ln. Now, let's differentiate both sides with respect to x. So the derivative of x ln x, we stated before that the derivative, right? So when we were doing this problem before, we had to find out the derivative of x ln x, and we got that it's equal to 1 plus ln of x. So let's write that down. So that's just going to be 1 plus ln of x. Okay, cool. Now, what's the derivative of ln of y with respect to x? How do we do this? This is another tricky part. When you're differentiating a function, in this case, we're differentiating x with respect to x. We do whatever rule that applies to this. When we're differentiating, in this case, ln of y with respect to another variable, then we actually have to use the chain rule. So imagine this, okay? You can think about this ln of y as a composite function, right? You can think about this as, so you have f of x, which represents your outside function. And the outside function, you can think about it as your ln of x. And you can have your g of x your inside function represented as y. So f of g of x is literally just going to be, well, it's going to be ln of x, but except, you replace all the x's with y's. So it's just going to be equal to ln of y. So you notice how ln of y can actually be written as a composite function. Now, what's f prime of x? What's the derivative of ln of x? We said that's equal to 1 over x, right? But it's f prime of g of x, and we know g of x is equal to y. So everywhere we see x, we would just replace it with a y. So it's going to be 1 over y times, well, the derivative of our inside function. So the derivative of g of x, or the derivative of y. So we're trying to find out the derivative of y. Well, that's just going to be equal to dy over dx, right? The derivative of y with respect to x is just going to be dy over dx. All right, y with respect to x. And now let's multiply both sides by y. So you're going to get the y's cancel out, so you get dy over dx is equal to 1 plus ln of x times y. We know that y, we said that y is equal to x to the x power. So we can substitute that in. We can distribute the x to the x, and we get that the derivative of y with respect to x is going to be equal to x to x power plus x to x ln x times ln x. And it's literally the exact same answer as I had before, right? It's the exact same answer as I had before.